How's it going, everyone? So in this video, we're going to talk about the vector cross product. So just to give a little bit of motivation why we're doing this, if you remember back to the series of lectures that we did on Tuesday, or whenever you're watching this, the first series of lectures for the week, we talked about how you can compute the moment of a force about a point using what we called the scalar technique. And in that scalar technique, one thing that we had to do was actually calculate the perpendicular distances. And that was the case where I was actually drawing or extending the lines of actions of the forces. I was going to the point of reference about which I was computing the moment, and I was considering all the lines from that point of reference to the line of action of the force and picking out the one that happened to intersect in a perpendicular fashion. And if we were lucky enough, and we were in all those cases, to actually be given that dimension, we could compute the perpendicular distance. However, what we're going to find is when we get to more complicated geometries, particularly when we get into 3 dimensions, that's going to be overly cumbersome. It's not going to be something that we're going to want to do often. Instead, we're going to rely on a generalized mathematical technique to do it the same way every time. And that is exactly what the cross product or the vector product, or even more confusingly, sometimes called the vector cross product, will allow us to do. So the reason we're learning what we're learning in this video is to actually be able to compute moments about forces the same way every time using vector techniques. So what is the cross product? Well, the cross product between vectors actually gives us a vector. So if you think back to previously in the course, we've already talked about a vector product, a way that you can multiply 2 vectors together. And that was the idea of the dot product or the scalar product. In that case, when you took the dot product of 2 vectors, you actually produced a number or a scalar. So the first thing that's different about the cross product is when we take the cross product of 2 vectors, we're going to get a vector. And when we think about a vector, it has a magnitude associated with it, and it has a direction. So let's begin by talking about how you actually get the direction of the cross product of 2 vectors A and B. And that's an actually right-hand rule that we've been talking about beforehand. And rather than actually try to show you using my right hand, I'm going to refer you to this figure. If you notice, the way that they have determined the direction of A cross B is to take the actual fingers of the hand, align them towards A, curl them towards B along the shortest separating angle, because if you think about it, you could curl in 2 directions. You could either curl along the short theta, or you could curl along the longer 360 minus theta, but curl in the shortest way possible from A to B. And naturally, the way that your thumb points, that's going to be the direction of C. So that's what that is showing you here. So you think about it, if this makes sense to you, ask yourself what B cross A would be. If you were doing B cross A and you started with your fingers on B and crossed A, it would actually point down or in the opposite direction in that sense. So that's how you get the actual direction of the cross product. How do you get the magnitude? Well, the magnitude of the cross product is related to the magnitude of both vectors that you're taking the cross product of, magnitude A, magnitude B. And in addition, it's related to the geometry separating the 2 variables, the 2 vectors, sorry. If the vectors are separated by some angle theta, then the magnitude of the cross product is going to be mag A, mag B, sine theta. So if you think about it, that's a little bit similar to how the actual geometric definition of the scalar product looked, only in that case, it was mag A, mag B, cos theta. So what's different about those 2 trig functions? What do you know about the sine function? Well, the sine function is going to start at 0, unlike the cosine function, which starts at 1, and it's going to increase all the way to 90 to 1 when the 2 vectors are 90 degrees apart. So what that means is that unlike the scalar product, which gave us the largest magnitude when the vectors were similar to one another or aligned mostly in the same direction, the cross product is going to give us a large magnitude when these 2 vectors are perpendicular to one another. And we'll see that in a minute. But if you think about that geometric definition that we just talked about, it's going to give us a lot of intuition about some basic cross product identities that we want to remember. First and foremost, what will be the cross product of a vector with itself? Well, if you're taking the cross product of a vector with itself, what angle actually separates the 2 vectors? There is no separation. So theta in that case is 0. And remember that the sine of theta, by definition, is 0. So what that means is if you take a vector and you cross it with itself, you're going to get 0. Yeah, these 2 terms won't be 0. However, since the angle between them is 0 and the sine of 0 is 0, the cross product of a vector with itself will be 0. What about rules for actually taking the cross product of the unit vectors along the x, y, and z axis, or you might call them the Cartesian unit vectors? Well, if you just use your little right-hand rule, and this is a good way to kind of test and make sure you're getting it. Notice here they're showing you that I cross j equals k. And you can do a similar thing. You could show that j cross k equals I. And it actually turns out that there's a pattern to it. And oftentimes that is represented in textbooks by these types of circles where you have the unit vectors I, j, and k. And what this is telling you is if you move in the counterclockwise direction and you take the cross product of 2 adjacent Cartesian vectors, for example, I cross j, you'll get a k. K cross I will be J. If you move in the other direction around the circle, you will get a unit vector as well, like k cross j will be I. However, since we're moving in the clockwise direction, which the way that they've laid out this tool, that corresponds to a negative sign, k cross j would be negative I. And actually, the way that I learned this was actually arranging them I, J, K, and clockwise positive. So if you have had a calculus course previously where you saw that, it's totally okay. Whatever little tool you remember to be able to compute those cross products is totally fine. Totally fine. So how do you actually, if you have a cross product, if you have two vectors and they're expressed in rectangular form in 3 dimensions, how do you actually go about computing a cross product? Well, if A has components, AX, AY, and AZ, and if B has components, BX, BY, and BZ, the way that we're actually going to compute the cross product is we're going to put them into a 3x3 matrix. So the components of A will go in the second row, the components of B will go in the third row, and then along the first row, we'll have the unit vectors I, J, and K. And sometimes, of course, you call them I hat, J hat, and K hat, since that hat means nothing more than it's a unit vector, which means that it has a magnitude of 1. The way that once we have the cross product kind of set up and structured in that matrix, the way that we're actually going to determine what the cross product is to take the determinant of that 3x3 matrix. And if you're familiar with determinants of 2x2 matrix, and we talked about that a little bit when we talked about Cramer's rule, when we first dealt with systems of linear equations, you know if a matrix is 2x2, the determinant is the difference of the downward diagonal product minus the upward diagonal product. However, in 3x3, it's a little bit different. You have to do what's known as a cofactor expansion. And what we're going to do is we're going to start in the upper left-hand corner, which would be the I element. We're going to cover up the column, cover up the row, and that's going to leave us with a 2x2 matrix. Well, we know how to take the determinant of a 2x2 matrix. It's just the downward diagonal product, AY times BZ, minus the upward diagonal product, AZ times BY, or you can write it in the other direction if you want, BY times AZ. Multiplication still commutes. What we're going to do is we're going to take that determinant and we're going to use it to be the magnitude of the I hat component of the cross product. Then we're going to move along that first row to the J hat component. We'll cover up the column of J, cover up the row of J, just like we did in the case of I, only now since we're in the second column, it's the second column that's covered up, but still the first row. And then that will leave us with a 2x2 matrix as well. And you notice when you cross those out, you're left with AX, AZ, BX, and BZ. And that 2x2 matrix, you can take a cross product of it. And that's exactly what they've done here. AX times BZ minus AZ times BX. However, the one thing I want to be careful, make sure that everyone sees here, and they have it in a box here to make sure that you remember it. As you're doing that cofactor expansion along the first row, when you do the expansion of the I term, that term is positive. When you do it for the J term, that term is negative. When you move over to the K term and you actually complete the determinant, that term is going to go back to being positive. So it's kind of like the signs. That's exactly what is happening. If the matrix was bigger, you would see that. But the signs are actually oscillating. It goes plus, minus, plus. And if you know linear algebra, you don't actually have to do this along the first row. It's just the most convenient way for our particular case of taking the determinant, since we need these basis vectors involved in our result. It'll be most convenient. And in fact, it's just 100% recommended to do your expansion along the first row. So let's talk about an example problem from this little section. We're given two vectors expressed in rectangular form. The first vector A has a x component of 1, y component of 2, z component of 0. The second vector B has an x component of -1, y component of 3, and z component of 0. And what we want to do is compute A cross B. And then we want to see if the result agrees with our physical intuition. So let me close that box, hit F1 on accident. I'll pull up my .cam and we'll talk about how we would take this product. Well, the first step that we want to do is actually form our 3x3 matrix. Remember that in our 3x3 matrix, in the first row, we'll put the 3 unit vectors along the x, y, and z axis, I hat, j hat, and k hat. In the second row, we'll put the x, y, and z components of A. And in the third row, we'll put the x, y, and z components of B. And then what we're going to do is we're going to move along this row step by step. And with each element, we will cover the row, we'll cover the column, and we'll get a 2x2 matrix that we take the determinant of. So let's do it for the I hat component first. The corresponding 2x2 matrix, if I cover the first row and I cover the first column, that I'm left with is just down there in the lower right corner. That's just going to be 2, 0, and 3, 0. That's the matrix that I'm left with. Now I'm going to write the entire expansion first, then we'll take the determinants. I'll move on to the j hat component. Remember that as you're moving along the row, the signs swap. It's plus, minus, plus. When you cover the second column, in the first row, you're left with the matrix 1, 0, minus 1, 0. And then go to the last, or the k-hat component, and you add that together. Covering the first row and first column, you're left with 1, 2, minus 1, 3. Now it's just a matter of actually taking these individual determinants. Remember, when you take the determinant, you take the product of the downward diagonal minus the product of the upward diagonal. So this is just going to be, and I'll write this in a big parentheses, 2 times 0 minus 3 times 0. So if you notice, this term is actually going to be 0. The whole thing will cancel. On the second term, we'll have minus j hat. We're going to take the product of the downward diagonal, 1 times 0. And then on the upward diagonal, it will be minus 1 times 0. And you see the pattern here. This is also 0 minus 0. There is not going to be a j-hat component either. In terms of the k-hat component, the sign switches back to a plus. This determinant, I'm not going to actually show it written out here. It's just 1 times 3, which is 3, minus 1 times 2, which is minus 2. And don't forget, minus is plus. So this cross product actually just simplifies down to 5k hat. So what we would say is that the vector A cross B has no x component, it has no y component, and its z component is just 5. And it doesn't have any units in this case because A and B don't have units. But let's think if this agrees with our physical intuition. Well, let's just sketch what A was. Notice that A had an, let me zoom out a little bit so you can actually see it, an x component of 1 and a y component of 2. So it's going to be over here. There is A. And notice that B had an x component of negative 1 and a y component of 3. There's B. So they both live actually in the xy plane. So remember what we said back to when we were talking about the scalar formulation of computing moments in the last video, and how whenever we had a copointer force system, whenever we compute the moments, they're going to be about an axis that is actually perpendicular to the plane. And that's exactly what we get here. And I'll move the document up. If I put my right hand on A, and I curl towards B, notice that my thumb is pointing right out at you. So if this is the x-axis and this is the y-axis, that cross product is going to be exclusively along the z-axis. And that is exactly what we get. And we'll say that this agrees with our physical intuition. So everything checks out. So hopefully that was a refresher for you. Maybe you've seen a cross product before. If not, I hope that at least for the three-dimensional case, you kind of see the pattern and the rule for how you actually determine it as how you actually compute the cross product, I should say, as the determinant of that special 3x3 matrix that we just showed.